Good morning, good afternoon, good evening, whatever the case may be. We are back in better than ever, and we are continuing our discussion about related rates. So this is related rates part 2. Let's get to it, shall we? Okay, so we've already done one example, and we got 2 more to go, and then we'll end it for now. What we have now is a cube that is expanding. So its volume increases at a constant rate of 10 centimeters cubed per second. Find the rate of change in its total surface area. So right away, we know that we are looking for the change in surface area. And if we let A represent our surface area, we are looking for dA dt. That's always one, you can always write that down, and it kind of keeps you focused on what you're looking for at the instant when its sides are 20 centimeters long. So first, let's sketch a cube. All right, beautiful cube. That's not a bad freehand square, kids. Look at that. Huh? Not as dumb as I look, although I'm not sure what that means. All right, so I'm going to go ahead and let x be the length of the sides of the cube. And what are we dealing with here? We are dealing with surface area, and we are dealing with volume. We're looking for dA dt, so let's get a formula that involves the surface area. Well, there's 6 sides to a cube, obviously, and the area of each side is x squared. So the surface area A is equal to 6x squared. So dA dt, and that's our goal, that's what we're looking for, is equal to 12x dx dt. And this is wonderful news because we're looking for the change in total surface area at the instant when its sides are 20 centimeters long. So we have x already. We have x equal to 20. Problem is we don't have dx dt, and right now we have no way to find it with what we have written. However, we know about volume, and it's increasing at a constant rate of 10 centimeters cubed per second. Well, the volume of this cube is equal to x cubed. And if I take the derivative with respect to t, dv dt is equal to 3x squared dx dt. Haha, there's dx dt. And I know the rate at which the volume is increasing. And that is 10 centimeters cubed per second, and it's constant. So I can substitute that in. We are looking at the instant when x equals 20, so that's 3 times 20 squared times dx dt. And you can use your calculator there, and it's not too bad without a calculator, but we know that dx dt is equal to 1/120th, I'm sorry, not 1/120th, sorry, 1/120th centimeters per second. This is wonderful news because we are pretty much done. We know what dx dt is. I'm just going to bring this formula down now, and so I am solving for dA dt, and dA dt is going to equal 12. And again, we're looking at for the instant when it's 20 centimeters long. So 12 times 20 times 1/20 using substitution. Totally legal because this change is constant. We use 20, and so we know that dx dt is 1/120. So 1/120 there, and that is approximately equal to, not approximately equal to, it's exactly equal to 2 square centimeters per second, and that's our answer. Okay, so it's just a matter of looking at what you have, looking for what it is you're looking for, and how you can get everything that you need that is missing, given the information that you have. All right, so now we have triangle ABC is right angled at A, and AB equals 20 centimeters. So I'm just going to go ahead and draw that real quick before I forget it. So it's right angled at A, right angle here, and AB is 20 centimeters. What else do we know? Angle ABC, so this must be C, increases at a constant rate of 1 degree per minute. I'm just going to jot that down. D theta dt, if I let theta be angle ABC, that's going to be 1 degree per minute. Okay. At what rate is BC changing? That is a length. So I'm going to stop there. At what rate is BC changing? So if I let BX or BC be represented by X, then I am looking for the change in X. Looking for dx dt. Bam! All right, let's go. At the instant when angle ABC measures 30 degrees. Okay. So what do we got going here? Got a right triangle. So it looks to me like we're going to have to use right triangle trigonometry because we're looking for our hypotenuse. We have an adjacent side there. And so I can use right triangle trigonometry. So what's the relationship that we have? Cosine theta is equal to adjacent over hypotenuse. And just for ease, since I know I'm going to be taking a derivative, I'm going to go ahead and write that as 20x to the negative 1. Okay, so if I take d theta dt, which is what I'm looking for, the derivative with respect to t, the derivative of cosine is negative sine theta d theta dt. And that is equal to negative 20x to the negative 2 dx dt. Because this is in terms of x, this is in terms of theta. I have theta. I'm looking, I don't have x yet, and I'm looking for dx dt. So now we have to find x. Well, we know if theta equals 30 degrees, and why do I use that? Well, because I'm looking at the instant when angle ABC measures 30 degrees. If theta equals 30 degrees, then I know that the cosine of 30 degrees is equal to 20 over x. That's root 3 over 2. So I'll go ahead and write it out step by step. Root 3 over 2 equals 20 over x. X is going to be equal to, you can, however you want to think about it, 20 over root 3 over 2, which is 40 over root 3, if we wanted to be exact, which we are going to go ahead and stay as exact right now because we're not solving for x, we're solving for dx dt. So you should not ever use a calculator estimate until the final answer, unless you absolutely have to. Okay, so now we have something for x. We have d theta dt. However, we need to change. We need to always calculate in radians. So I'm going to change 1 degree to radians. So that's times pi over 180 degrees. The degrees cancel, so that's equal to pi over 180. 1 degree is equal to pi over 180 degrees, which makes sense. Pi is equivalent to 180 degrees. All right, so now we're in business. So using this formula and everything that I have found out, negative sine 30 degrees. Because again, we're looking for at the instant when ABC measures 30 degrees, times d theta dt. Well, 1 degree per minute is equal to pi over 180. And that is equal to negative 20. X to the negative 2, I'm going to go ahead and put that in the denominator for ease of calculation, I suppose, squared, because x to the negative 2 becomes x squared, multiplied by dx dt. And I'm solving for dx dt. I'm not going to do all of this work here. I'm hoping you're able to do that with your calculator. You better know that sine of 30 is 1/2, so that's a negative 1/2. And I will just tell you, give you the ending to the story if you enter this in your calculator correctly. Dx dt is about 0.233 centimeters per minute, meaning that the length of BC is changing at a rate of 0.233 centimeters per minute when theta measures, when angle ABC measures 30 degrees. All right, so again, you just need to draw a nice picture, figure out what you have, and figure out what you're looking for. Then you get formulas that include what you're looking for, or I should say a formula, and use any other mathematics or formulas that you need to get all of the missing things. We had d theta dt. We knew theta was going to be equal to 30 degrees. We needed to find x, and we found x using right triangle trigonometry. All right, hope you enjoyed it. I know I did. And with that, I am out.
There's across the window hides the line, but nothing hides the color of the lines that shine.